Thanks for the introduction, Gabor, and thanks for the invitation to come here. I'm going to talk about cost functions somewhat intrinsically induced on affine manifolds, and then I'll compare them to these get from relatively independent bases, which Yang Li has been talking about. So everything I say today will be joint work with Sohaib Khalid. And I think I'm going to go straight at it here. So I think this is a somewhat summary of the starting point I want to take here. So first of all, existence of these canonical bases by Bloom and Liu, together with Yang Li's recent work, proves the metric SYC conjecture. So in other words, given a polarized maximal generation of Calabi-Yau manifolds, we have, there's this, for all delta larger than 0, we know that for small enough t, we have a special Lagrangian torus vibration on a subset of our Calabi-Yau manifolds, which are of sort of Calabi-Yau measure, almost all Calabi-Yau measure, 1 minus delta. And then the point of these canonical bases then, or one point of them, is that they induce a cost function, a canonical cost function. Namely by us taking evaluation of the corresponding basis element. And rather, so what you really do is you take, I should put this in quotation mark because it's there's also a limiting procedure involved in this, but it's not important at the moment. And then Yang Li, so he combines this with non-Archimedean geometry, so very loosely speaking here. And so let me see. So there are two things I want to say here. First of all, the sort of one thing that non-Archimedean geometry gives you, or resolution of the non-Archimedean Calabi-Yau equation, is that you actually produce something which is a semi-positive metric in the sense of non-Archimedean geometry. So this is approximable by Fubini-Study metrics, which is central point in this argument. Another point here as well is there's actually an interplay here between the non-Archimedean geometry and the optimal transport, also when it comes to produce the solution to the actual real Monge-Ampere equation, to actually show that the real Monge-Ampere, that the non-Archimedean potential actually solves a real Monge-Ampere equation. There is methods from optimal transport combined with some deep results in non-Archimedean geometry, namely an orthogonality principle. Of the non-Archimedean Monge-Ampere operator. The second thing I want to say here is I want to say something about this UT. So the sets where we actually get these special Lagrangian torus vibrations. So they are one way to describe them. I think the best way to describe them is to describe what do they map down to in the essential skeleton. So they map into sort of relatively compact subset of a certain set E of the essential skeleton, which is a full measure. And then this set E here, it's picked so that it avoids certain kind of pathological areas. So on the one, first of all, it avoids the lower dimensional phases of the essential skeleton. It also avoids the singular locus or the corner locus of the tropical theta functions you get from the relatively independent basis. And in terms of optimal transport, it avoids points with 2 or more conjugacy points, so points that maps where the C gradient is multivalued. It avoids points mapping to the boundary of a certain Okounkov body, which is constructed as well in the argument. And it also avoids the singular set of local solutions to Alexandrov-Monchamp equations. So, so some remark about this is that the codimension of the complement is 1, while a general expectation is that you might be able to do this on a set with codimension 2, or away from a set of codimension 2. Also, this set E is not connected and it's not explicit. And the reason I listed these here is because I want to illustrate that essentially all of these points here give rise to quite different types of questions. I think, for example, the first point here, it has to do with the question of given a maximally degenerate family of Calabi-Yaos, how to specify an affine structure near the vertices. And I think this is probably something which needs input from the algebraic geometry of the family. So this is kind of a soft question. The further 3 questions here, I think, will need some kind of input, both from algebraic geometry and optimal transport theory. Somehow we need to, while the last one is really, in a sense, a pure PDE questions. There's there are many different things that needs to be addressed. So, and to somehow summarize, I think for a more detailed understanding of this vibration and this set E where it lives, there are 2 things that I think we need. On the one hand, a polyhedral space dual to the essential skeleton. That's something that's given for free in this toric setting that Rolf was talking about earlier today. And this is also something that's closely connected to an affine structure near vertices of SKX. And also more information, or possibly even explicit information, about the cost function. And I should say that in this talk now, I will not sort of address this at all. I will only talk about this part down here. So I will work entirely in this toric setting. So Y is going to be a toric Fano manifold, and we're going to look at families of hypersurfaces in Y. So in particular, then we're going to have a moment polytope. And it's dual. And I would also mention, as you work, so this moment polytope, it lies naturally in a vector space, usually called MR, which is, yeah, it's a vector space, so it's isomorphic to Rn for some n. And the dual polytope, then it lies in the dual space, which is often denoted NR. So this is the dual. That means there is also, we also have a pairing, which we get from this ambient setting, ambient toric funnel setting. Namely, we get the pairing between these two vector spaces. From the perspective of optimal transport, that sort of provides a natural cost function. This is also the cost function that give these results, which Rolf talked about earlier today. And one point I want to make with this in this talk then is that this is not the correct cost function. In general, this needs to be modified. And you can actually see this quite quickly if you start looking at examples. So this is the example of the Fermat family of cubic curves in P2. So here the moment polytope is a polygon. It looks like this. It has a certain number of lattice points. It has 1 interior lattice points and 9 lattice points on the boundary. And sort of the toric framework here, it tells you that if you take the each lattice point here corresponds to a monomial, and these monomials actually gives a basis for this space of holomorphic sections over the ring of the field of formal Laurent series. So somehow we get the basis immediately, a very natural basis. And this is also the basis if you use it to construct a cost function, then you get precisely 1 minus the pairing. However, this basis is not valuatively independent. To see this, you need to do a small computation. So one example of 2 elements which are not relatively independent are these 2. So the bottom one there is the monomial z x squared. The top right one there is the monomial z squared y. And what valuatively independence means. So a basis is valuatively independent if a basis is relatively independent at a point n in the essential skeleton if the valuation of some linear combination over this field of formal Laurent series is the same as the minimum. This should be true for all coefficients. And then valuative independence then in general means that it should be valuatively independent everywhere on the essential skeleton. So, and then when I say that these 2 are not valuatively independent, then what I'm saying here is that if I pick a point here on this face of the essential skeleton, then at that point these are not valuatively independent. So to compute this valuation given by this point, we take whatever we have here, we expand it as a function of y and z. So I think there's a typo here. This should not be dx, this should be the z. And then we take the vanishing order in z plus the vanishing order on y of the leading term. So here we get x, we ignore x, we just put x equal to 1. So the vanishing order of C is 1 here, so I get 1/2. I don't have any vanishing in Y. And if I check if I compute the valuation of Z squared Y, I get 2/2 plus 1/2, which is 3/2. However, if we look at this locus, so near Y equals C equals 0, then we look at the following combination. So, or first of all, near this locus, we have that T, using this equation, defining our family. We know that T is Y times C over 1 plus Y cubed plus C cubed, which I can expand. So I get 1 plus Y cubed plus C cubed plus Y cubed plus C cubed squared, and so on, probably with a minus sign here. And if I compute the valuation of the following element, I take T times C x squared minus C squared Y. Then I expand whatever I have in the expression I have in there. I get Z squared Y times 1 minus 1 minus Y cubed minus C. I hope I got signs right here, but if I got the signs wrong, it's just a matter of either adding or subtracting this thing. The point here is that when I add this, I take this linear combination with T, then the leading terms are going to cancel. So this is going to ruin this equality here. So we arrive at same valuation, but at the terms we get from here, which is Z to the squared, Y to the power of 4 minus Z to the power of 5 times Y plus higher order terms, which is 3. So relative independence here fails because we get cancellation when we expand near this locus where Y and C is 0. The solution then to this problem, it is to replace one of these basis elements with a perturbation to it. We add a correction. So instead we replace this one by the expression here. Then we also know from this computation as well what the leading term is. So if I replace this monomial with this one, then I will get something which actually evaluates to 3 in this point. And then we sort of proceed by symmetry because we need to have this property for all phases of our essential skeleton. So you can sort of proceed and do the same correction to all of these terms. And then you will actually end up with a relatively independent basis at this level. So at level 3 for this line bundle. And if you do that, then you can plot what does the cost function, or you can try to infer what is the shape of the cost function based on this information. As you evaluate this point in monomials on this phases of the polytope, you get just the corrections will not interfere at all, so then you just recover the pairing you started with. So you get something which is 0 here at the orange point, and it's going to be 3/2 here at the other 2 points. And then, so this is for these 2 phases. But then we also found that if I evaluate this basis element up here, I get 3. So I get the value 3 in these 2 points. By symmetry, I will get the same in over here. And if we compare this, so let me draw what I would get from the usual pairing here. Then I would get this cost function. So we see already at this level, at level 3, if we produce a relatively independent basis, we already diverge from this pairing that you would pick, that you get if you take the naive basis. So we got information about the cost function in all the lattice point here. So here, here, and here. Not quite up here, but you could possibly infer that it's going to look like this between these 2 points. So this might or might not look mysterious, but I want to point out a couple of things that I see in this thing. First of all, I see some kind of convex singularities here. They all have the same weight. They all have weight 1 and 1 and 1 here. So these kind of appear. And as you compute the relatively independent bases for higher values here, this cost function actually preserves, like this shape preserves. So these are, you could think about these as prescribed singularities. And then I want to think about this concave singularity as a cut locus of some kind. And it will be clear later on why I want to think about it like that. And then I want to explain how this cost function actually arises intrinsically from the affine structure of the central skeleton. And then I'll present sort of a general construction which works for all polytopes. And then some kind of evidence for why this is natural. I have 2 results, or we have 2 results, me and Sohaib. The first one is that for P3, so we can produce a relatively independent basis, and it gives exactly this cost function. And the second one is that for general polytopes, there is a way of producing, at least in examples, there is a way of producing solutions to real Monge-Ampere equations in the same way as you get from the solution to the non-Archimedean Monge-Ampere equation.
Well, it's the question. So does it mean if you take now instead of 3, you take 4, 5, 6, etc.? I mean, that would give the same cost function.
Yeah, that's. So another point here as well is that if I would, so now what I did now is maybe a bit backward, but I fixed a point in the essential skeleton, and then I drew what the corresponding kind of figure would be, or graph would be as a function on the moment polytope. I think what people use, like the theta functions, are usually the other way around. You fix a point here and look at the function here. But it's quite symmetric. But let's say I move this point a little bit. What happens to this shape then? And what's going to happen is that you get a something where you have exactly the same prescribed singularities, convex singularities of weight 1. And then you have a cut locus, but everything is kind of tilted a little bit. So in particular, if you look at the difference between these 2 cost functions, then you get something which is affine on a pretty large subset of the essential skeleton. Okay. before I get into kind of the details of how to set up that cost function or define that cost function, I want to say something about like a more general thing, which I think is interesting. So orthogonality principles in optimal transport. So as a kind of a model case of an orthogonality principle, I fix a bounded convex set in Rn, and then I look at convex functions. So I look at a convex function which such that the gradient image of this is equal to k. So I look at the second boundary value problem. And then I take a compactly supported continuous perturbation, G, and I perturb my F a little bit with this. And then I define the convex envelope of this perturbation as just double the Legendre transform. So it means if my F plus G looks something like this, so F is convex, but F plus G might not be convex. And then when I take a convex envelope, I take the supremum of all its supporting hyperplanes, so supremum of all linear functions which are bounded above by it. So then I get something like this. And then what this principle says is that the support of the Monge-Ampere measure of the envelope lies on the contact set. So wherever these two things doesn't touch, so wherever I have this kind of concave region which disappears when I take the envelope, the Monge-Ampere is zero. That's like a classical principle. You could envision similar principles in optimal transport. So let's say you have two, if we'll work pretty generally, so we take Polish topological spaces and a continuous cost function, and then we fix a target measure. So typically this should have some nice behavior, like be some kind of Lebesgue measure, absolutely continuous or so. Then you could ask if this data satisfies the orthogonality principle, which would mean that if I take some continuous potential, and then I take its double C transform, which is the equivalent of doing this, taking some C convex envelope of it, and I look at in general, it's not so easy to define the Monge-Ampere measure for general cost functions. But so I think the correct condition to put on this is that the envelope of phi should be the Kantorovich potential of the corresponding optimal transport problem. So we have this equality here that phi CC actually maximizes this functional. Then I want to say that the mu is supported on the contact set here. Get back to these orthogonality principles near the end of the talk as well. Okay, so to set up this cost function, so the way I think about it, it should kind of hold for all mu, but of course you could say that, you could ask if it holds for all absolutely continuous mu and so forth. Okay, so to set up this cost function then, I'm gonna talk a little bit about affine manifolds first. So an affine manifold is a topological manifold of dimension n. But an affine manifold of dimension n is a topological manifold of dimension n equipped with a distinguished atlas, such that the transition functions in this atlas are affine. So we have regions here where we have coordinate charts. And of course, we have an overlap in our manifold. And then the transformation that transforms this region from one set of coordinates to the other should be affine. these also come in particular more kind of less generally. An integral affine manifold. It is the same thing, but where the transition functions have a linear part in GL and C, so integral coefficients. In particular, that means if you have such a structure, so the transition functions lie here, that means that the transition functions are volume preserving. The determinant is 1 or -1, which means that you have a well-defined Monge-Ampère operator on this manifold. So you can compute the Monge-Ampère expression in coordinates, and it's going to be equal no matter which coordinates you pick. Maybe I should write SLN. It depends on. All of these will be in SLN anyway, all of the examples I have. So starting with the reflexive polytope. So a reflexive polytope is this data you get from a toric Banach manifold. So it's a lattice polytope, such that its dual is also a lattice polytope. We actually get affine structure not on all of the boundary, but on almost all of the boundary. And the way to do that is the following. So if I have a polytope and I pick a vertex of that, then I can look at the quotient map, where I take the quotient of the line spanned by this vertex. And then I get something, and I restrict this map to the star of V, in other words, all the faces containing V in the boundary of my polytope. That means I have something from, so this is a topological manifold of dimension n-1, and I have this map down to the quotient space of dimension n-1, so these are my coordinates. And if you do this for different vertices, then they induce compatible affine structure on the open faces. So I can do this, let's say I do this for the triangle. Then if I do it for this vertex, this is my star. It will map down to, it's a line segment down here. If I do it for this vertex, this is my star. It will map to this line segment, and they have sort of a common face here. And then the induced transition function here will be affine and volume preserving. If I try to do this in higher dimensions, it almost works. It works to a certain extent. So these coordinate charts you get, they will be compatible on open faces, which means, so this is what Rolf explained as well previously. If I pick the coordinate chart corresponding to this vertex, I can include all of my faces in the star, open facets, and I can include part of this edge. But then when I produce a coordinate chart around this vertex, I can include all of these open faces, but I can sort of only include part of this edge, because these two coordinate charts, they cannot overlap on lower dimensional faces. So what happens is that you get an affine structure on the boundary after excluding a subset of codimension 2, and this subset of codimension 2, it should be picked so that it divides each n-2 face into one component for each of its vertices. So in the 2D example here, that meant we need to pick a point on each edge that splits the edge in one part for each endpoint. In the three-dimensional case, it means we pick these trivalent graphs on lower dimensional faces of our polytope. One important point here is that this in general, it's not quite clear how to pick this subset. I mean, it's clear that it needs to satisfy this to get an affine structure, but apart from this, it's not clear how to pick it. You could imagine having something piecewise affine or something which could behave in any way a priori.
Put the higher could filter.
So I mean, the singular set will kind of intersect them in general. You probably get something similar there, that they will probably be split as well. I think it kind of follows. Yeah. I will also talk about something which is less standard, which I will call an affine polarization, mainly because I think the data I'm using here comes from the polarization of the toric of the family, the polarization of the toric Fano manifold. So from this data, in particular from the moment polytope, we can get for each the following data. So for each vertex in the essential skeleton, and each facet in the star of this vertex, so each facet which contains this vertex, we get a function which is 0 on this facet, and it's affine on the entire star. And I also get such functions that has the following compatibility condition, namely that if I take the difference of two such functions corresponding to two different facets, then this is affine on the entire star. And the way I do this, I just pick this, I use the pairing, and for each facet I pick the corresponding vertex in the moment polytope of that facet. So this is data that kind of just falls out from the toric setting. But this data is essential when I construct this cost function, and this is also the data that prescribe these singularities we saw, the prescribed singularities in the cost function we saw earlier. Another piece of affine geometry is affine continuation and development maps. So we take an affine manifold which is simply connected, and then I have an affine function which is defined in a small open set in this one. Then this affine function has a unique extension. You can produce it. It's like an elementary construction. You just look in each coordinate chart and you extend it in that coordinate chart. And because it's simply connected, you will never run into you will never get any contradictions when you do this. There's always just one way of doing it. And if you do that, so locally, it's easy to come up with n linearly independent affine functions. If you do that and you extend all of them, then you get a map into Rn, and that's called the development map. So, and this is, in fact, uniquely determined, or it's canonical, up to left composition with an affine transformation. Also universal in the sense that whenever I have an affine map on my manifold X, it factors through this development map. So it kind of encodes how all affine functions behave on my manifold. So the kind of core idea of this cost function that I'm going to define, it is the fact that, well, on Rn we have the pairing, and we have a map. Whenever we have a simply connected affine manifold, we have a map to Rn, so we can just pull back the pairing, and then we get the cost function. However, the affine structure we have on the boundary of our polytope, it's not defined everywhere. So the actual affine manifold we have is not simply connected. So what we want to do is we want to work on the covering space when we do this. On the other hand, I don't want to fix the location of my singularities before I define my cost function. Like I want actually the location of the singularities to somehow arise from the optimal transport problem. So we don't do it. We don't use the traditional covering space. Instead, we define a kind of synthetic covering space, which we work on instead. And then, of course, we construct something on the covering space. It's not going to be well defined on the manifold, and that's one point where we use this polarization data to get something which actually becomes well defined downstairs. So to construct this covering space, we consider something we call visiting sequences in our polytope. So first of all, we fix a vertex of our essential skeleton, and we fix a vertex of the moment polytope, and we do this in such a way that they are sort of conjugate in the sense that the scalar product is 1. So V0 lies in the phase corresponding to W0 and vice versa. Then a visiting sequence in the boundary of the essential skeleton. It's a sequence like this of vertices and facets interchangeably. Such that whenever I have something adjacent here, they are incident. So any vertex lies in the faces preceding it and that comes and succeeding it. I also assume that I don't have two vertices appearing, the same vertices appearing twice just after each other. And the same thing for faces. I don't want the same face to appear twice. And then at the end of the sequence, I have a point which lies in the last facet here. What this means is that I have some base point in my polytope, and then I consider paths where I go from this base point to a facet, to a vertex, to a facet, to a vertex, to a facet. In terms of affine geometry, it means that I move across this facet, and then when I go into the next facet, I use the coordinate chart I get from this vertex, or the coordinate chart close to this vertex, and so forth. These actually represent the actual paths these represent the possible paths I have in my affine manifold if I would fix the location of my singular set. And then I construct my covering space here by, first of all, I look at such sequences of a fixed length, and then I limit of this k tends to infinity as the length tends to infinity. So I also want to add a little bit more. So I'll call it a visiting cycle if the last point here is sorry. We say I want to call it a visiting path, and I will denote it by gamma if X is a vertex, and it's a visiting cycle if X is the same as the base point. Then what you get in this construction is a polyhedral complex. It's not going to be a topological manifold because you can sort of near one edge like this, you can kind of go back and forth like this through interchanging vertices. What you'll end up with a space where this edge actually has an infinite number. It's an edge of an infinite number of faces. So it's not a topological manifold, it's not locally finite. But there is a map down to the boundary of the simplex, and this is unramified on open faces at least. We also have the group of, well, the visiting cycles form a group, and this acts on this covering, and it acts transitively on the fibers of this map. So it works really as a covering space. And one thing which becomes very, I mean, somewhat more transparent here is that the fundamental group of the polytope and its dual are isomorphic. There's a natural isomorphism on these elements where you just replace every vertex with the corresponding face and every face with the corresponding vertex in the duals. So we have one group here, pi. One fundamental group for both polytopes. Okay. Of cost function then. Then there is a unique function on the product of the covering spaces, which satisfies that for any 2 points and any visiting paths gamma and gamma v in our polytope and its dual respectively, we have that the following expressions is affine on the so for any, so what I have here is a, let me draw something. Let's say I have some path which ends in this facet. Then what these properties tell us here is that if I fix, so let's say this is my essential skeleton, so the dual polytope, and I fix a point in my moment polytope, I fix an M, then this tells me that as I move into the next phase here, my cost function is affine up to this term right here. So I use these terms. These are my f tau, which I used before. I use this term to create, to achieve these prescribed singularities. So this cost function is really given by affine continuation, but also introducing these singularities on each edge, these prescribed singularities. And I get the same statement, but dual. So I get the same behavior in terms of by fixing a point n. And then I also, the final property I prescribe here is that on the face, on the faces dual to my base points in my 2 polytopes, this should be given by just the standard pairing. So if you do this, then you get something which is continuous. And it's also invariant under the diagonal action by this fundamental group. If I move around in my polytope along a certain path and I do the same thing in my dual polytope, then I get the same, then I have the same cost for those 2 points. It's also has also bilinear in a certain sense. Namely that if I look at, if I think about this as a function in M and N, I have my cost here, and then I subtract these elements, kind of reference elements. If you remember in Yang Li's talk, he usually didn't consider just this as the cost function. He would sort of subtract same thing, but for some reference point y. Somewhat for similar reasons we do this. That you need to do this to get something which actually looks like a bilinear function. They admit what kind.
You said it, so I think there's some developing now. Some finite.
Yep, they do. So they have pure dimension, infinite, but they have pure dimension. So yes, yeah, that's the way to think about it. Or like a book, like you have many pages on one axis kind of. And so they, in the same way as a simply connected affine manifold, they have a development map. Yes, okay. That means if I still have some time left, yeah. If I go back to this image here, so here we had these prescribed singularities, but we also have this concave singularity, which I refer to as a cut locus. And the reason you get this thing is because you get this thing because you take to go from the covering space to the something that's defined on the manifold. We will take the minimum of this. So to define it on a point on the manifold, we just take the minimum over all fibers. I will say that a polytope is of finite type if there is a collection of facets in the covering space, the subpolyhedral complex, which is preserved under diagonal action by pi and which is finite modular this action, such that when I take minimum over all points in, so this should actually be in gamma, not in the product, mapping down to m and n, then I get a function which is continuous and which is also concave in a correct sense, which is given by this. I'm gonna show in two examples what you get. So first of all, or maybe I'll see if I should say something more here. So this is just what I did here. I want to say that this expression here is concave. So this is I look at this locally in the star of MT and the star of N sigma. And what I've done here is I've just subtracted these kind of things that erases these prescribed singularities. And after erasing the prescribed singularities, I want to end up with something concave. That's what this condition means. Okay, so for this, in this example, P2, then I want to fix a number of faces in my covering space such that I can take minimum over this and get something which is continuous and concave, locally concave. So let me do this so let me first fix a facet of my moment polytope. Let's call it sigma. And then I'll tell you which facets lie in the slice, kind of parallel to the slice defined by sigma. So this will be facets in the covering of the essential skeleton. And so I'll put my base point up here. And then I'll include this face and this face. And I'll include this opposing face twice. Once by getting there from this direction and once by getting there from this direction. If I draw this in the graph here, that means I'm including my two faces here. They are different faces. And this one and this one are actually the same. But I include them twice sort of by reaching them from two different directions. So this thing here is two instances of this phase. And then we also see that if I take minimum of this function that I got here, then I get something which looks like this. Which is just a slightly squeezed version of the image I had before. And we computed a relatively independent basis. If in P3, so I first fix a facet of my moment polytope here. And then let's say I have my base point up here. Then I want to include all of these facets in gamma in the slice there. So I get 3 of those. Let me see what color I used. Yeah, so I get 3 of those. So these are distinct facets downstairs as well. This would correspond to, so let's see, how did I draw this now? Yes, this would correspond to sort of this face, and the one at the back. While the one at the bottom, I include 3 times. I actually include it 6 times because I can reach it in 6 different ways here. I can go through this face and through either this vertex or this vertex, or essentially I have 3 different faces to choose from and 2 vertices to go through in each face. So I could, for example, go here, then here, and then into that one down there. So this corresponds then to 6 different addresses, if you will, in this covering space. So if you use this gamma, and you take the minimum over these faces in the covering, then depending on which point you pick in this face, you will get only 3 of these 6 instances of this face will be relevant. And if I draw this, so let me draw the moment polytope from, like, looking at it from this direction down here. Now I have my V0 up there. Then I get a cut locus that looks like this. So for all the other faces, there is only one term competing here. So they will all be, the cost function will be affine here. But then on the last one, there will be a cut locus. There will be 3 competing affine functions on it. And then as I move my point here, the exact location of this cut locus will change. And if I move my point move it into another phase, there will be sort of a discontinuous change as well. The cut locus moves into another phase. So the main theorem then is that the Fermat family of cubic curves admits in relatively independent basis for all k, so you don't need to look at large enough k. It really, you can actually construct it for all k. It's also explicit, so you can easily compute the cost function, and the cost function agrees with the one you get from this construction and the one I drew before.
Well, okay, I mean, if you take K1, you get something.
You do, and I think to get the, if we look at the, so let's go back here. So here I looked at level 3. That meant I can compute the cost here, 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 and here. If I do it at, so I mean, if I would just interpolate directly, I would get something that looks like this. But already, if you compute it at level 6, you will also get this point here. So then you actually get this cut locus up there. Then, I mean, of course, like, so if you compute it for a particular level, then you only know it, you know its value above exactly that point. If you want to know it, say, in a neighborhood of a point, you would need to consider, you'll get points of arbitrarily large denominator, so you need to consider arbitrarily large k. So to actually know the cost function, you need to compute, you need to produce a basis for all k. Yeah, but you. I don't think so. I mean, I don't know. That's not the way we do it. We do it for all k. Of course, after a certain level here, after level 6, the cost function will not change. I mean, if you do a procedure where you compute a relatively independent basis for a certain level, and then you just interpolate linearly between them, then you could ask, did I get the correct cost function now? And from level 6, you do. Or if you have something which is divisible by 6, then you do. Yeah, it is. It has, in some sense, minimal cut locus as well. You could imagine something which is piecewise linear but has a lot of cut locus, but it seems in this case it's just 1 point. So if there's no more questions about that at the moment, then I'll say something about orthogonality principles as well and solutions to real Monchampere equations. So once you have this cost function on the covering, if I fix 2 points, or if I fix 1 point in the covering of my moment polytope, then I get a set in the, well, I get a set, so this is not very precise. I should write that n comma m0 should lie in gamma. Then I can look at the set where the cost function on the covering achieves its minimum. This will be, if I look downstairs, this will kind of encode the slope in that point of the cost function. So it will play the same role as the Konko bodies does in Yang Li's argument, or a similar role. So you get the sets in the covering spaces. And when you have these sets, it turns out that the orthogonality principle holds if and only if the development maps are injected on these sets. So for this cost function, there is actually a way to, in examples, verify whether or not the orthogonality principle holds. And if the orthogonality principle holds, then you can solve real Monge-Ampere equations to the same extent as Yang Li does with using the non-Archimedean Monge-Ampere equation. So if I have something which is of finite type and the condition in the previous theorem hold, then I pick a measure which has the same mass as the total mass of my dual polytope, of the boundary of my dual polytope. Then there is a set of full measure and a potential which solves the real Monge-Ampere equation in the Alexandrov sense on this set. And then this injectivity of these development maps, it can also be, with some work, it can be verified in examples. So I mentioned that you had this for the unit simplex, you had this cut locus on one of the faces, which divided the face into 3 different regions. If you look at where they are what they're mapped to by the development map, you get a figure like this. So one of them is mapped down here, the other 2 up here, which means they map injectively to R2, this region. That's also, but it's somehow this can be sort of checked in examples, but it's unclear how to verify it for any larger class of the polytopes. And I think I'll stop there.